Lab 1, constant velocity. So the purpose of this lab is to demonstrate Newton's second law in action by analyzing the motion of an object rolling in a straight line after being pushed using tracker software. This observational data is compared to computational data, which is our predicted data from a constructed computational model of the observational data on Glowscript. This predicted data is predicting what the ball would move like with zero net force acting on it. By comparing the predicted and observed data, we can see that velocity is constant when there is no net force acting on the object. Models used are Newton's first law: an object at rest will stay at rest unless another force acts upon it. Newton's second law: net force is equal to mass times acceleration, and constant velocity, which happens when there's no net force acting on the object. So force equals mass times acceleration. We also use velocity average, velocity update formula. I did this both for my calculations and also for the computational model. Position update formula, again, for my calculations and the computational model. In this experiment, you can pretend that the change in velocity is equal to initial velocity because we are at constant velocity. So in this experiment, the object observed is the TB12 massage ball pushed by my hand on a lab table. Because friction and air resistance are being ignored, the only two forces acting on the ball are gravity and normal force, which cancel out, making a net force of 0. This means that the ball is assumed to have a constant velocity in the x direction. So the velocity used in my computational model is an average over the first 5 time intervals from my observational data points found using tracker. Here are some figures demonstrating what is the force diagrams on the ball. The one that we're really going to focus on is the one on the right, showing the normal force and gravity canceling out and just focusing on the constant velocity of the ball. The middle one shows how the ball went from rest to motion, and the one on the left shows what's really going on. There is friction and air resistance that will cause it to have a non-constant. Here's my video using tracker. You can kind of see that the ball is a little wobbly. This is due to the grooves on the surface. This will cause a non-constant velocity in addition to friction. So the system is the TB12 massage ball. The surroundings are the table, my hands, and the air. Here's some of my experimental data. What I want to focus on is the final position, which is negative 0.456 meters. This is negative because the ball is moving from right to left. The change in time is 0.835 seconds, and the initial velocity, which is equal to the final velocity because we are, again, pretending there's no net force acting on it, so we're at constant velocity, is negative 0.556 meters per second. And the net force is 0. Here's my computational model. We used the velocity update formula right here and the position update formula right here to model our predicted motion of the ball. Delta t is 0.033 seconds. And then you can kind of see the predicted model for the ball. The position versus time graph is linear, so that kind of shows that the velocity is constant. And again, you can see with this horizontal line, it is at constant velocity. Comparing our observed versus predicted data, they are pretty similar. They're pointing in the same direction. They're pretty close together. The observed data is poking out a little bit behind the predicted data, so it is not actually at a constant velocity. And you can kind of see in this velocity versus time graph that it is not constant, and this is because we are ignoring the air resistance and friction that are actually happening. So some sources of error, we are ignoring air resistance and friction, so that will definitely impact the velocity of the ball, but also the texture of the ball will cause it to is causing it to roll in a not straight line. I also did not perfectly use tracker when I was plotting my data points. In conclusion, the computational model was a good predictor for the motion of the ball since the graphs were pretty similar between observed and predicted data. Tracker was slightly inaccurate due to human error, and observed data differed since air resistance and friction were ignored. If tracker software was used perfectly and the ball was smooth, on a small time interval, the data